Our first presenter today is Teng, who is a senior at St. Edward's University, majoring in mathematics. She's been working with Rachel Swanson, Dave Barnett, and Nora Kotalko on a project for the SIM data product and creating a public-facing R package. So Teng, whenever you're ready, we can get started with your presentation.
Hey, sweet. Thank you, Zach. Okay. All right. Thank you, everyone. Thank you for being here. So neon sites span a wide variety of habitats, many of which are affected by natural events such as fires and droughts, as well as human activities such as logging or grazing. While some of these disturbances are captured through neon's regular sampling, many are not fully reflected in our existing data products. So neon staff have been systematically documenting both unexpected disturbances and site management actions at all aquatic and terrestrial locations, although these are not scheduled sampling protocol like other data products at Neon. But this information is available as a Neon data product called Site Management and Event Reporting, or SIM for short. And this data offers important context for interpreting Neon data and helping us understand how events and other land management decisions may influence data collected at Neon. And Neon continues to update and share this information through their data portal regularly. So SIM has a technical working group, which is made up of experts who review the product and advise on strategies with the goal of improving quality and usability of this disturbance data. There were various challenges, and along with that came recommendations on how the data product could be improved. But the most strongly emphasized was to collect spatial data directly in the field. Unfortunately, that approach is too expensive to implement. So as an alternative, the development of an R package to help users was suggested and approved for the summer, which is how this project came to be. So like Zach mentioned earlier, our main goal for this summer was to create a public-facing GitHub repository for our new SIM R package completed with documentation. So we developed a few key functions, including one for summarizing our data and another for working with it spatially. So let's begin with our summarize function. Our summarize function is designed to simplify the SIM dataset, and it summarizes the data by event, year, site, event type, and location type. And an event ID is essentially a unique identifier that Neon assigns to each disturbance or management activity that is recorded. So in this example, you can see a single event ID spans 3 rows, and that's because this event lasted several months. And Neon splits long events to match their date publication format. So when you're looking at a larger data set, you might see repeated rows for the same event, which can make things a little harder to interpret. So this function takes in the data frame along with optional parameters as site name, event type, and location keywords. And the goal is to take this dense data set and return more digestible summary tables to help users quickly understand and get an overview of what is going on. So in this example, I ran the function, gave it a few filters, and this first table is a summary of the filtered results. Total records is the number of records, so there are 279 rows in the data set that match those filters. Unique events is going to be the number of unique event IDs, so 279 rows represent 66 different event IDs. 2 unique events because we're only filtering for fire and grazing. The second table breaks down by event type and site. So for example, there were 54 fire-related records from these 2 sites, 12 from CLBJ and 42 from Disney. Now this third table breaks things down by year, site, and shows total records and unique events recorded each year. And this last table breaks the data down by site, event type, and location keywords. Together, these summary tables help us understand the when and where of these disturbance events. So now let's take a step further and look at how we added spatial context to our data. We ended up splitting our spatial function into 2 separate functions, one that handles drawing the polygons and another that writes those polygons into shapefiles. And separating the 2 make the code more modular and easier to use depending on what the user is looking for or needs. So to create the polygons, we first need to get the actual location or spatial data for each row in the SIM data. So the location ID currently just contains all the locations. It doesn't include any spatial information like coordinates. So before running this function, the user has to run the data through another Neon R package called GeoNeon to get the spatial information necessary. Once we do that, the column changes. Instead of a bunch of words, now each entry now becomes a little table, also known as a little nested column. that includes information of latitude, longitude, elevation, dimensions, etc. And this allows our function to turn point lists into real polygons by giving us spatial information necessary for mapping. And once we've added the coordinate information using GeoNeon, we can generate polygons using a package in R called SF. And our function simply pulls the coordinates from the nested columns, and SF does the rest for us. It connects the dots in order and creates a polygon object for us. Now the function itself takes the GeoNeon process data frame as a parameter. So to do this for multiple events, we set up a for loop within our function that runs through each unique event ID in the dataset. For each, it pulls the spatial information, builds a polygon and a buffer using our data in SF, and creates a basic leaflet map to show it. Each polygon, as well as its corresponding data, is also saved as an SF object, which is essentially just a way to store spatial data. And the polygons, leaflet maps, and SF objects are returned in their respective lists for easy user access later. And your polygons will look different based on how many valid coordinate points you have. Now, for some special cases, our function will just find and pull the correct predefined boundary polygon from separate files and upload it into our GitHub repository. And it handles auto logic like checking if the site is terrestrial or aquatic and applying extra conditions when needed. And this still gives us usable polygons for mapping and analysis. But now that we've generated our polygons, the next step is to write them down as files. And this lets the user take the spatial data and use it in other tools like GIS software or other mapping platforms. It also makes it easier to share and store the polygon data for future use. So to make this easy, we created a mini writer function that takes in the list of SF objects created from our polygon function and writes each one into a shapefile on the user's computer. This way, users don't have to manually save each file, and it automates the process and keeps everything organized. Now, once the function is ran, it should look something like this on the user's end. To show how this can be used in practice, here's a side-by-side view of the same polygon. On the right is going to be the leaflet map generated in R. And on the right is going to be a leaflet map. On the left is going to be the same polygon, but loaded into a GIS software called ArcGIS from the shapefiles we exported. And this shows that our workflow not only builds and visualizes spatial data in R, but also makes it fully compatible with external GIS platforms. Now here's another side-by-side view, comparison of the individual polygons we created from one of our sites in Oregon called Abby. Similarly to the last slide, leaflet maps on the right and the same polygons imported into ArcGIS as a full shapefile layer on the left. Now this next slide shows how our manually generated polygon lines up with existing spatial data. You can see the neon site boundary and the US Forest Service logging activity data, which is those dotted lines within the boundary. Our polygon fits neatly within the boundary, which helps demonstrate that our spatial output is built accurately and well aligned with official land use data. So overall, we built a workflow that takes the sim data to something that's summarized, spatially visualized, and ready to use in R or other GIS platforms. It handles a variety of edge cases, creates reliable outputs, and helps users better understand the context and location of disturbance events. That being said, building all this wasn't without its challenges. There are definitely areas for improvement and future development. One of the biggest challenges for me was that I never built an R package before, so learning how to do that and structure that, it was very challenging. And on top of that, I've never worked with spatial data before, so this summer I got to familiarize with tools like SF and leaflet and shapefiles. But honestly, that made it really fun for me because it pushed me to learn new things in a short amount of time. But now that we have a working package, there are some ways this can be expanded and improved. Additional functions, writing a data tutorial to help users get started and use the package, and completing our documentation and publishing it to the public and possibly to CRAN to make the package officially available and easier for anyone to install and use. These would help expand the reach of the tool to make it more valuable to researchers, educators, and data users across the NEON community. Thank you.
Great job. Thank you, Shu. Excellent work. All right, I put some stuff in the chat. You can either use the Q&A functionality or you can raise your hand and we will unmute you. So we have a couple of minutes to take some questions for Shu. There is one in the Q&A from Paul. It says, it looks like each row only stores a single lat-long pair. How is a polygon constructed from that? Also, do all the rows for the same event share the same lat-long?
Can you repeat the first part of the question?
Yeah, so it says each row in the data frames that you showed have a single lat-long, so single set of coordinates.
Mhm.
How does that turn into a polygon in the final product?
Some of them are really close to each other, so they look the same, but they're not all the same points. But basically, when R grabs all that coordinates, it will reorganize it for you in order and basically draw that polygon out for you. Like I didn't have to do any of that myself.
And so the second part of the question was, do all the rows of a single event share the same lat long? Sounds like the answer is no, right? They're probably different.
No, yeah.
Right. Awesome. Thank you. Any more questions? We have a question from Kate. Says, excellent work and presentation. Is it possible to capture uncertainty in the polygons, uncertainty in the coordinates, and make that go into the polygons?
Yeah, for sure. An example here. Oh, maybe not. Well, there's a couple of missing rows of data in there where you just have to skip those rows. But there are some aquatic sites where the polygon kind of skips like all the curves in between and kind of just skips down and doesn't include all of the aquatic like sites. Yeah.
Give another few seconds for any more questions to come in.
I think I'm unmuted. Can you guys hear me?
Yeah, we can hear you.
Cool. Hey, Shu, it's Paul. So Mike, I'd asked the question about the lat long, but can you click back to that slide that showed after you pass it through? I think it was GeoNeon. After you pass it through and it takes the data frame and extracts it to lat long. So, right, my question was right here. So for any given row, there's only one latitude and longitude. So then is drawing those polygons, you take all of the rows for that event and you connect all of those polygons in like a convex hull, and then it makes up, or you connect all those pairs and it makes a polygon. Is that right?
Yeah.
So then I guess I didn't quite understand why. I know that one event can have many rows, but what does each row in that event correspond to? Is it just to have the different lat long points, or is there another more information captured by different rows? Does that make sense?
Like repeat that again.
So I can see right now, for example, on that bottom data frame, I think these are all the same event. Is that
Yeah,
correct?
that's the one
Okay.
event.
And so I can see there's different information, like some say current, true or false, some have different elevations, blah, blah, blah. So then what you're doing, if I understand it, is you're taking all of those latitude, longitudes, plotting each one to get a bunch of points, and then you connect all those points, and that gives you your polygon. Is that right? So then, okay, I'm at, my question is getting too long here, so I'll be short at this point. So, like, for example, let's take the first row is current, says current true. Second row, current is false. So then does that latitude, longitude for the first row mean something at that location is current and something at that second location is not current? Is that right?
I should have left that column out. We didn't really use that current column.
Okay, gotcha.
Yeah.
So basically the rows are so you can store and make polygons. Sounds like the main point of it. Okay, cool. Thank you, Shu.
All right. Great job, Shu. Thank you very much, and great work this summer.
Thank you.